Electricity and magnetism are interrelated and are also interconvertible. Let us look at a few examples. In this setup, an electric current passing through a conductor produces a magnetic field, which can be observed through the deflection of a magnetic compass needle placed near the conductor. This proves that moving electric charges produce magnetic fields. Electric motors work on this principle. However, in this setup, we see that an electric current is induced in a closed coil when subjected to a changing magnetic field. The phenomenon in which an electric current is generated by varying magnetic fields is called electromagnetic induction. Electric generators work on this principle. We will now discuss and learn about 3 experiments by Faraday and Henry relating to electromagnetism. In the first experimental setup, a coil is connected to a galvanometer. When a bar magnet with its north pole facing the coil is moved towards or away from the coil, the galvanometer needle deflects to the right and left side of 0 reading respectively, showing the presence of a current in the coil. Now, let us see what happens if the south pole of the magnet faces the coil. The galvanometer needle deflects to the left side of 0 reading as the magnet approaches the coil and deflects to the right when the magnet moves away from the coil, showing the presence of a current in the coil. The galvanometer needle deflects only as long as the bar magnet is in motion. Once the bar magnet comes to rest, the galvanometer needle settles down at 0 reading, indicating that there is no current in the coil. From all these observations, we can conclude that whenever there is relative motion between a bar magnet and a coil, an electric current is induced in the coil. In the second experimental setup, there are 2 coils. Coil 1 connected to a galvanometer, coil 2 connected to a battery. Due to the steady current in coil 2, a steady magnetic field is set up around the coil 2, and this magnetic field is also linked to the coil 1. When coil 2 is kept stationary and coil 1 is moved towards coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the left of 0. When coil 2 is kept stationary and coil 1 is moved away from coil 2, a current is induced in coil 1 and the galvanometer needle deflects to the right of 0. If we keep coil 1 stationary and move coil 2 towards coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the left of 0. Now, if we keep coil 1 stationary and move coil 2 away from coil 1, a current is induced in coil 1 and a deflection is observed in the galvanometer needle to the right of 0. From all these observations, we can conclude that whenever there is relative motion between a current-carrying coil and a closed coil in which a galvanometer is connected, a current is induced in the closed coil. In the third experiment, a tap key is provided in the coil 2 circuit. Here, we can observe the deflection of the galvanometer needle even when the 2 coils are stationary. This deflection is observed only at those instants when the tap key is either switched on or off. This happens because of the change in magnetic field during switching on and off. When a ferromagnetic material like an iron rod is placed coaxially along the two coils, the effect of the magnetic field linked to the coil 2 increases due to the nature of the ferromagnetic material, as it allows more number of magnetic lines of force to link within the area of the coil. Hence, the deflection of the galvanometer needle increases, indicating an increase in the induced current. Before attempting to understand Faraday's law of electromagnetic induction, we should recapitulate the terms used in electromagnetic induction. These terms are representation of a surface area by a vector A, uniform magnetic field B, and magnetic flux phi B. The area of a plane surface is represented by a vector A drawn along the outward normal to the plane surface. In the case of a curved surface, the surface area is split into very small areas, and each is approximated to a planar area. In a uniform magnetic field B, the number of magnetic field lines cutting across an area placed perpendicular to the field lines is same for each unit area of the surface. If a plane of area A is placed in a uniform magnetic field B with its area vector A, making an angle theta with the magnetic field, then the magnetic flux phi B through the area can be written as phi B is equal to B dot A, which is equal to BA cos theta. Let this be equation 1. Magnetic flux phi B can be varied by changing any one or more of the terms B, A, and theta. The SI unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux phi B is a scalar quantity. When the magnetic field has different magnitudes and directions at the various parts of a curved surface, the magnetic flux through the curved surface is computed by extending equation 1. Phi B is equal to B1 dot dA1 plus B2 dot dA2 plus and so on, which is equal to sigma all Bi dot dAi. Let this be equation 2. So far, we have recapitulated the terms used in electromagnetic induction. Let us now learn about Faraday's experiments where we use these terms. Faraday conducted 3 experiments, from which he concluded that an EMF is induced in a coil when the magnetic flux cutting across the coil changes with time. In the first experiment, Faraday observed that the relative motion between a magnet and a coil changes the magnetic flux across the coil. This change in magnetic flux with time induces an EMF in the coil. Similarly, in the second experiment, he observed that the relative motion between the two coils, one carrying a current, changes the magnetic flux across the coils. This change in the magnetic flux with time induces an EMF in the other coil. In his third experiment with 2 coils, he found that if the tap key is pressed, the current in coil 2 and the resulting magnetic field rises from 0 to maximum value in a short time. This results in a change in the magnetic flux with time across coil 1, inducing an EMF in it. If the key is kept pressed, there is a steady magnetic field across coil 1. Thereby, there is no EMF induced in it and the current drops to 0. When the tap key is released, the current in coil 2 decreases from a maximum value to 0 in a short time, resulting in the magnetic flux across coil 1 to drop suddenly, thereby inducing an EMF in it. From the observations of these 3 experiments, Faraday concluded that the time rate of change of magnetic flux through a closed coil induces an EMF through it, and stated the Faraday's law of electromagnetic induction. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. We can put this law in the form of a mathematical equation. E is equal to minus d phi b divided by dt. Let this be equation 3. In this equation, E is the induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. When n number of turns are closely wound to form the coil, the change of flux with time for each coil is the same, and we can write for the total induced EMF as E is equal to minus n into d phi b divided by dt. Let this be equation 4. In this equation, E is the total induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. Therefore, the total induced EMF can be increased by increasing the number of turns n of the coil. Before attempting to learn about Lenz's law, let us first recapitulate about the right-hand grip rule applied to a current-carrying coil. Consider a right-hand fist with the thumb extending out. If the fingers are wrapped in a circle pointing in the direction of the current through the coil, then the thumb points towards the end of the coil, indicating the north pole. Lenz's law helps us in identifying the polarity of the induced EMF in a coil. Lenz's law states that the polarity of induced EMF in a closed loop is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. We can put this statement in simple terms. If a current is induced by an increasing flux, it will weaken the original flux. If a current is induced by a decreasing flux, it will strengthen the original flux. The magnitude of the induced EMF is given by Faraday's law, which is E is equal to minus d phi b divided by dt, where E is the induced EMF in the coil and phi b is the magnetic flux. The negative sign in this equation represents the effect as stated in Lenz's law. Let us look at Faraday's experiments and apply Lenz's law to them. To identify the polarity of the induced EMF and the direction of induced current in the coil. In this experiment, the coil, which is connected to a galvanometer, is at rest. A bar magnet with its north pole facing the coil is moved towards the coil. This causes the magnetic flux through the coil to increase. A current is induced in the coil which opposes this increase in flux. The induced current is in a counterclockwise direction, looking from the bar magnet side. This current produces a north polarity towards the north pole of the magnet and opposes the motion of the magnet, thereby opposing the increase in magnetic flux through the coil. A force is required to move the magnet against this repelling force. The same magnet, when moved away from the stationary coil, causes the magnetic flux through the coil to decrease. A current is induced in the coil which opposes this decrease in flux. The induced current is in a clockwise direction looking from the bar magnet side. This current produces a south polarity towards the north pole of the receding magnet. This south pole attracts the north pole of the bar magnet, thereby resisting the motion of the magnet. When the south pole of the magnet is towards the coil and it is moved towards the coil, a south polarity is induced near the south pole of the magnet. When the same magnet is moved away from the coil, a north polarity is induced near the south pole. In all these experiments, we can also use an open circuit in the place of a closed loop. In this case too, an EMF is induced, but there is no induced current in the coil. The direction of this induced EMF can be found using Lenz's law. Here is an easy way to understand the direction of induced currents and EMF. We have so far taken Lenz's law for granted. Suppose that the induced current is in the direction opposite to the one given in the figure. In that case, the south pole due to the induced current will be near the approaching north pole of the magnet, causing the bar magnet to be attracted towards the coil. A gentle push on the magnet will start the process of motion, and its velocity and kinetic energy will continuously increase without expending any energy. If this is true, we can construct a perpetual motion machine with a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. So, we can conclude that Lenz's law is correct. In all the experiments discussed, a force is required to move the magnet bar either towards or away from the coil. The product of the force and the distance moved gives the work done on the magnet. The work is done by spending some mechanical energy by the person conducting the experiment. The mechanical energy is converted to electrical energy in the coil. The electrical energy is converted into heat energy by heating up the coil, which is dissipated into the atmosphere. From these observations, we can say that the energy is only converted from one form to another, or the energy is conserved. We have studied about induced EMF in a circuit due to the rate of change of magnetic flux through the circuit. This happens due to the relative motion between the coil C1 and the bar magnet. We know that the induced EMF E is equal to minus d phi by dt, where d phi by dt is the time rate of change of the magnetic flux and the minus sign is in accordance with the Lenz's law. Let this be equation 1. Now let us study about induced EMF produced due to the motion of a conductor in a magnetic field. Consider PQRS to be a rectangular metallic loop having a galvanometer G connected between R and S. The part PQ can slide forwards or backwards in between the parts PS and RQ of the loop. Let us now place PQRS in a uniform magnetic field such that its plane is perpendicular to the magnetic field. For a time-independent magnetic field, the magnetic induction B remains constant both in magnitude as well as direction. Let the length of PQ be L and that of RQ be X. Let the conductor PQ move towards the ends SR with a constant velocity V. We observe that the conductor PQ, the direction of the magnetic induction B, and the velocity V of the conductor are mutually perpendicular to each other. we see that the conductor initially is at a distance x from the RS end. As the conductor moves towards the RS end, it is displaced from its original position and its velocity v can be written as dx by dt. Since the plane of the loop is normal, that is, perpendicular to the magnetic field, maximum magnetic flux passes through the loop. This magnetic flux, phi b, passing through the loop is equal to the product of the magnetic induction B and the area A of the enclosed loop. The product of L and X represents the area swept A. Hence, we can now rewrite the magnetic flux phi B as equal to BLX since A equal to LX. As the conductor moves towards the RS end, we see that X is varying and hence the area A enclosed by the loop also changes with the time. Therefore, we see that magnetic flux phi B also changes with time as the magnetic flux depends on the area enclosed. Hence, according to principle of electromagnetic induction, an induced EMF is developed across PQ. This induced EMF, E, is equal to minus d phi b by dt as given by equation 1. Substituting for phi b, we get E is equal to minus d by dt of BLX. As B and L are constant and only X is the variable, we can write E is equal to minus BL into dx by dt. As dx by dt represents the velocity v of the conductor PQ, we can write electromotive force E is equal to minus BLV. Let this be equation 2. The induced EMF E is also called the motional EMF in this case. The concept of motional EMF can also be explained by using the Lorenz's force acting on the free charge carriers of conductor PQ. We know that when a charge Q enters perpendicular to a uniform magnetic field of induction B, then the Lorenz's force on the charge FB is equal to QVB. As the conductor moves with a speed v, free electrons in the conductor also moves with speed v in the magnetic field B in addition to the random velocity they have within the metallic conductor PQ. The average magnetic force due to the random velocity is 0. But the average magnetic force on each free electron due to velocity v is Fb equal to QVB, where Q is the charge on the electron equal to minus 1.6 into 10 power minus 19 coulomb. From Fleming's left-hand rule, we can say that in this situation, the magnetic force on a positive charge moving with velocity v in this magnetic field will be along PQ. In accordance with the same rule, we can see that the force on the electrons Fb will be directed along QP. And we see that the free electrons in the conductor move towards P. As a result of this movement, a negative charge builds up at P and a positive charge appears at Q. An electric field is developed within PQ such that the electric field exerts a force Fe equal to QE on each electron. In electrostatic equilibrium, the force Fe will be equal to Fb, and this build of charge stops. Since Fe becomes equal to Fb, we have QE equal to QVB. Simplifying, we get E equal to Vb. Due to the charge buildup, a potential difference is developed across PQ, which is the induced EMF E. We know that the potential difference E is equal to E into L. Substituting the value for the electric field strength E equal to VB, we get induced EMF E equal to BLV. Since Lenz's law is obeyed here also, we can write this induced EMF as E equal to minus BLV. This induced EMF E is the motional EMF. Due to the induced EMF, an induced current flows in the closed loop PQRS, and the current can be detected by the galvanometer. This induced current flows along the path QRSP. This equation for the motional EMF derived in this manner is the same as the equation 2 which we derived earlier. Now, consider the case when the conductor PQ is stationary in the magnetic field, but the magnetic field varies with time. That is, its magnitude or direction, or both magnitude and direction are changing with time. Since the conductor is at rest, its velocity v is equal to 0, and as seen earlier, the magnetic force Fb equal to QVB is 0. The moment the magnetic field starts varying, an induced current flows in the loop which can be detected by the galvanometer. Since the magnetic field force Fb is 0, the electrons are forced to move only by the electric field, and hence we conclude that an electric field appears instantaneously. This electric field is produced by the changing magnetic field and is called the induced electric field. This electric field causes an EMF to be developed in the loop, and hence an induced current flows in the loop. From these observations, we can say that just like the moving charges in a conductor can produce magnetic fields and exert a magnetic force on a magnet in its field, a varying magnetic field can also exert a force on stationary charges. So, if we move a bar magnet towards a stationary charge, the charge experiences a force due to the varying magnetic field. This is the fundamental significance of Faraday's discovery. Consider a rectangular conducting loop PQRS placed in a uniform magnetic field of strength B. The arm PQ of the loop can be slit over its arms PS and QR. Arms PS and QR of the loop are part of the rails SM and RN connected to SR. The length of SR is L. The length of the arm PS at an instant is X. Let the electrical resistance of PQ be R. Let us assume that the resistances of the rails SM, RN and the link SR is negligible compared to the resistance of arm PQ. Hence, the overall resistance of the rectangular loop is R. The flux through the loop at any instant, phi B, is equal to the product of the strength of the magnetic field B and the area enclosed A. Here, area of the loop A is equal to the product of the breadth and length of the loop L and X. In this case, the instantaneous flux phi B is equal to BLX. Let this be equation 1. From Faraday's law, we get induced EMF E is equal to minus d phi B by dt. The negative symbol is in accordance with Lenz's law. On substituting phi B from equation 1 and simplifying, we arrive at the equation E is equal to minus dBLX by dt. The strength of the magnetic field B and the length of the arm SR of the loop L are constant. Hence, the equation transforms to E is equal to minus BL dx by dt. But dx by dt is the instantaneous velocity v of the arm PQ of the loop, which is directed towards the SR part of the loop as shown. Hence, E is equal to minus BLV. Let this be equation 2. This EMF is the motional EMF as discussed earlier. As the resistance of the rectangular loop is R, the magnitude of the induced current, I, is equal to the magnitude of E by R. The current is directed from P to Q in the arm. Substituting the value of E from equation 2, we arrive at the equation I is equal to BLV by R. Let this be equation 3. As the current carrying arm, PQ, is in the magnetic field, there exists a force on the arm. The direction of this force acting on the arm PQ is given by Fleming's left-hand rule. According to the rule, the thumb, the forefinger, and the middle finger of the left hand are stretched such that they are mutually perpendicular. If the forefinger and the middle finger indicate the directions of the magnetic field and direction of the current respectively, the thumb indicates the direction of the force. Thus, as per the rule, the direction of the force on PQ is opposite to the direction of the motion of the arm PQ. Vectorially, the force on the arm PQ is given by F is equal to I L cross B, and this force arises due to the drift velocity of charges, responsible for the current along the arm and the consequent Lorenz's force acting on them. Hence, the magnitude of the force F is equal to ILB sine theta, where theta is the angle between the directions of the current and the magnetic field. Here, the angle between the arm PQ and the magnetic field is 90 degrees. Hence, the equation for the magnitude of the force transforms to F is equal to ILB sine 90. As sine 90 is equal to 1, this can be rewritten as F is equal to ILB. Let this be equation 4. On substituting equation 3 in equation 4 and simplifying, we get F is equal to B square L square V by R. Let this be equation 5. This force arises due to the drift velocity of the charges through the arm PQ that are responsible for the current and the Lorenz's force on them. If we need to maintain uniform velocity for the arm PQ, we need to apply a constant force F in the direction of the velocity. The applied force must be equal in magnitude and opposite in direction to the magnetic force. Thus, the power required to push the arm PQ along the rails is given by the equation P is equal to FV. On substituting the value of F from equation 5 and simplifying, we get the equation P is equal to B square L square V square by R. Let this be equation 6. Notice that the work done in moving the arm PQ is mechanical in nature. This mechanical energy is converted into heat energy when the work is done. This energy, referred to as joule heat, is given by Pj is equal to I square R. On substituting the value of I from equation 3 and simplifying, we get Pj is equal to B square L square V square by R. Let this be equation 7. Notice that the right-hand sides of the equations 6 and 7 are equal, thereby confirming the law of conservation of energy. Thus, mechanical energy which was needed to move the arm PQ is converted into the induced EMF and then to thermal energy. Thus, we conclude that the induced EMF in a conductor when moved in a magnetic field is in accordance with law of conservation of energy. Let us now study the relationship between the flow of charge through the arm PQ and the flux. From Faraday's law, we have learned that the magnitude of the induced EMF modulus E is equal to change in magnetic flux delta phi B by delta T. Let this be equation 8. However, the EMF induced in the circuit is equal to IR. But rate of charge flow is current. Hence, current can be replaced by delta Q by delta T. Let this be equation 9. The left-hand sides of equations 8 and 9 are equal. Equate the right-hand sides to arrive at the equation delta Q is equal to delta phi B by R.